Alright, today we're presenting the portable CRISPR-based diagnostic device for sickle cell disease screening. My name is Jake, this is Calvin, that's Mason, and this is Josh. Alright, for a bit of background on our project, today we're presenting about a portable CRISPR-based diagnostic device for sickle cell disease, which right now is one of the most common hereditary disorders in the world, yet many communities still don't receive any early testing. In low resource areas, people often aren't diagnosed until symptoms become severe. And even in the US, affordable genetic screening can still be hard to access. Our project focuses on creating a low-cost, portable approach to help make early diagnosis more equitable.
Our target audience includes individuals and families associated with sickle cell disease. Over 100,000 people in the U.S. live with SCD, most of whom are African American, and over 20 million people are affected globally. Many of these communities lack access to early genetic screening, which leads to delayed diagnosis, higher childhood mortality, and more serious long-term complications. Our design aims to support these underserved groups.
So for our challenge statement, sickle cell disease still remains undiagnosed due to many factors such as slow research studies, expensive costs, and limited laboratory equipment. Especially in low-income regions where this disease thrives, they don't have the resources to actually study this disease, so this disease still remains undiagnosed. And even in the more advanced healthcare systems, it's still limited study due to high costs again and limited specialists. So because of these reasons, we are developing a way to access a more portable and easy tool to study this disease.
So our solution is a portable CRISPR diagnostic device that can quickly detect the HBV gene mutation responsible for sickle cell disease. It uses CRISPR-Cas12 or Cas13 enzymes and works with a small microfluidic or paper test strip. With only 1 drop of blood, the device generates results in about 30 minutes. It doesn't require refrigeration, lab equipment, or trained specialists, making it ideal for rural clinics or mobile health workers.
And for how the device works, the process starts with a fingerstick blood sample placed on the microfluidic strip. The CRISPR enzymes inside the strip search for the SCD mutation. If it's present, the reaction produces a visible signal, and a handheld reader interprets the signal and shows a positive or negative result. This allows accurate genetic screening without a full laboratory setup, giving communities a reliable way to diagnose SCD early.
And so how this connects to the grand challenge that we have? This project connects directly to the grand challenge of engineering the tools of scientific discovery, and this is because our device expands access to molecular diagnostics in places that traditionally lack this technology. It supports earlier diagnosis, improves patient outcomes, and increases the amount of reliable genetic data to researchers. By doing this, it helps undeserved communities benefit from modern biotechnology.
So here are some of the existing technologies that we use to base our project on that prove that our project is actually feasible. So the 3 main ones that we base it on are the CRISPR Sherlock N detector, the Oxford nanopore, and the microfluidic paper-based diagnostic. And basically these 3 come together to form our technology and prove that our system is actually possible for solving this disease.
Each test cartridge is estimated to cost between $5 and $10, making widespread screening affordable. A pilot program, which includes research, manufacturing, and training, would cost around $3 million. This project aligns well with the funding priorities from the World Health Organization, the Gates Foundation, and the NIH Sickle Cell Program. Partnerships with companies like Thermo Fisher or CRISPR Therapeutics, which support large-scale production.
And some design challenges with this is regulatory approval will take time, and healthcare workers in some regions will also need training on the device. Supply chain issues could affect distribution in remote areas, and we also have to consider the community concerns around genetic testing and privacy. We plan to address these with education programs, partnerships, local clinics, and overall outreach to build trust and awareness.
Broader impact and the next steps going forward. Our device can eventually be adapted to detect other genetic conditions such as thalassemia or G6PD deficiency. Moving forward, the next steps include building and refining a working prototype, starting clinical testing with partner hospitals, and improving accuracy based on field data. After that, we would expand manufacturing and develop digital reporting tools to support health agencies.
So here are some of our cited resources that we use to develop our research and content.
Thank you for listening to our presentation.
You're welcome.